Hi everyone, and welcome to this grade 9 mathematics lesson where we will be exploring identifying linear functions. My name is Miss Donnell Phillips. Let's get started. So a linear function is pretty much just a function whose points lie on the same straight line. When we think of linear, we should think of line. We can identify linear functions by observing their graphs, their ordered pairs, and their equations. So in the first picture, the one with the green graphs, these are all linear functions. The second picture, the one with the red graphs, these are nonlinear functions. In both graphs, both of them or all of the graphs are functions. However, only the one with the green are linear functions and the one with the red are nonlinear functions. Graphs. When graphed, no point will fall directly under each other, and when connected, the points will form a straight line. So when we're looking at the graphs of any function, in order to see if it's a linear function or not, we should do two things. After we finish plotting the points, we should ensure that none of the points fall directly under each other. And then, when we connect the points, they should form a straight line. Now, we can observe that sometimes when we put a function on a graph, that some of the points don't fall under each other, but even when we connect them, they don't form a straight line. They're still functions, but they're just not linear functions. Example: identify whether the graph represents a function and explain. If the graph does represent a function, is the function linear? So let's look at the graph. We could see that each domain value is paired with exactly one range value. But the graph is not a line. It is a function, it is just not a linear function. Next, identify whether the graph represents a function and explain. If the graph does represent a function, is the function linear? So by looking at the graph, we could see that the only domain value, -2, is paired with many different range values. Even though it is a straight line, the points fall directly under each other. So it is linear, but it is not a function. The third example, when we look at this graph, we can see that each domain value is paired with exactly one range value. The graph does form a straight line when we connect the points. So it is a function and it is linear. Therefore, it is a linear function. Ordered pairs. You can sometimes identify a linear function by looking at a table or a list of ordered pairs. In a linear function, a constant change in x corresponds to a constant change in y. All this is saying is that if we look at the x values in a table, as we go down the line, there is some constant increase or some constant decrease. And if you look at the y values, as we go down a line also, there is a constant increase or a constant decrease. So in this table, a constant change of plus 1 in x, as we can see, we went from -2, -1, 0, 1. This means that as we go down the line, all of the x values are increasing by +1. And if you look at the y values, they are decreasing by -3. We went from 7 to 4 to 1 to -2. So a constant change of +1 in x corresponds to a constant change of -3 in y. And these points satisfy a linear function. Let's look at this next example. For the x values, we have -2, -1, 0, 1, 2. And we can see that we are increasing by 1. But if we look at the y values, we have 6, 3, 2, 3, 6. This is not a constant increase, neither is it a constant decrease. So in this table, a constant change of +1 in x does not correspond to a constant change in y. These points do not satisfy a linear function. The points from this table do not lie on a line. So if we were to graph this, we could see that the points, they don't fall directly under each other. However, when we connect them, they don't form a line. So this is not a linear function. Example, tell whether the set of ordered pairs satisfies a linear function and explain. So the x values, we have 0, 4, 8, 12, and 16. And for the y values, we have -3, 0, 3, 6, and 9. If you look at the x values, we can see that as we go down the line, each point increases by 4. And for the y values, as we go down the line, each point increases by 3. So there is a constant change of +x in x, and that corresponds to a constant change of +3 in y. So these points satisfy a linear function. Next example, if we look at the x values, we have -4, -2, 0, 2, 4, and the x values are all increasing by 2. But if you look at the y values, we have 13, 1, -3, 1, and 13. It is decreasing by 12, and then the next one is decreasing by 4, and then it is increasing by 4, and then increasing by 12. This change is not constant. So a constant change of 2 in x does not correspond to a constant change in y. These points do not satisfy a linear function. Equation. Another way to determine whether a function is linear is to look at its equation. A function is linear if it is described by a linear equation. A linear equation is any equation that can be written in the standard form shown below. Here we have the standard form. That is ax plus by equals c. A, b, and c are constants, and the x and y are just variables. When written in the standard form, ax plus by equals c, a, b, and c are constants, and a and b are both not zero. When an equation is written in standard form, x and y are not multiplied together. So if you ever look at an equation and you can see that the x and the y are multiplying together, this means that it could not be a linear function. X and y both have exponents of 1. This means that x could only be raised to the power of 1, and y could only be raised to the power of 1 also. So by looking at an equation, if there is ever x to the power of 2 or y to the third power, this means that these are not linear functions. And lastly, x and y do not appear in exponents, denominators, or radical signs. So if you ever see an equation and you can see that something is being raised to the power of x, or something is 1 over y or something in the equation is the root of xy, then these are not linear functions. Example, determine which of the following are linear functions. The first equation we have 5x plus 4y equals 7. Now if we look at it, we can see that it does satisfy being in the standard form of ax plus by equals c. So this is a linear function. In the second one, we have y is equal to 2x squared minus 3. The first thing that you should notice is that x is raised to the power of 2. Now we can recall that in the equations of linear functions, both x and y could only have exponents of 1. However, here we see that the x has an exponent of 2. This means that this equation is not a linear function. Next we have y subtract 2 is equal to negative 5x. For simplicity, if you were to change the subject of the formula and make the constant the subject of the formula, you would realize that it is actually in standard form. So y minus 2 is equal to negative 5x is the equation of a linear function. Next we have 8 plus 5 over x is equal to 7y. The first thing we should notice is that the x is a denominator. And in the equations of linear functions, we can't have the x or the y being the denominator of any number. Next we have y is equal to 9x plus 2. And yes, this is the equation of a linear function. Lastly, we have x times y is equal to negative 6. What did you notice? Yes, the x and the y is being multiplied in this equation. And for the equation of linear functions, we can't have the x and the y's being multiplied together. So this final equation is not the equation of a linear function. So to summarize today's lesson, functions whose points lie on the same straight line are called linear functions. We can identify linear functions by observing their graphs. When graphed, a linear equation will have a straight line that has a constant slope. Ordered pairs. In a linear function, a constant change in x corresponds to a constant change in y. And equations. A function is linear if it is described by a linear equation. A linear equation is any equation that can be written in the standard form of ax plus by is equal to c, where a, b, and c are constants and a and b are both not zero. I do hope I was able to shed some light on how to identify linear functions. My name is Miss Donnell Phillips. See you next time.